And then share my screen. Can everybody see my screen?
Yep.
Okay, perfect. Let me. Okay, let's me minimize this. All right. Yeah. So as we mentioned, we are in the finishing up the 4th week. Just to recap, the first week we worked on getting the database installed and being able to export databases. We talked about then we spent a week about how to design databases with class diagrams with boxes and arrows and whatnot. And then we spent about a week on how to create those databases using the create statement, where we can create relationships between various tables, one-to-many, many-to-many, and so on and so forth. And this week we've been spending time on how to retrieve data from a database, assuming that somebody had inserted in data. Next week we'll talk about how is it that we can actually update, insert, and manipulate that data. So let's finish up the material for today and for this week. And also there is a quiz that was made available earlier this today, and will be available all day today and then again tomorrow till midnight. Okay, and it's about it's about creating databases. So questions such as how to create a table, how to create a foreign key, a primary key, how to reference another table, and all that, right? And if we give you 2 tables and we say that there's a one-to-many relationship between one and another table, how would you implement that using SQL? Okay, so it's all questions about how to create tables. It's 30 minutes, and I think it's like 4 or 5 questions, something like that. All right, so let's finish up the material for this week. We had covered much of SQL queries from last time. We had talked about the select from where clause. That's where we're going to be spending most of our time on retrieving data from the database. We said that it was a statement that allowed us to zero in on a subset of records that met a specific criteria from perhaps many dozens of tables with thousands of records, identify those records that met a particular criteria. Throughout the semester.
Professor?
Yes.
I don't know if that was just me, but it cut out.
Okay. Yeah, let me know. I moved over, I've moved closer to my router just because I was having connections, but hopefully that's not happening anymore. But yeah, let me just keep me up to date on that, please. Hopefully I'll get less of that. And let me bring up the chat just in case. Just ping me on the chat if you can't hear me. Let me minimize this. Okay. Yeah, so we talked about, first we looked at the commands that were dealing with single tables. We saw that we can rename those tables for convenience, maybe shorten the name of the tables or make them more readable, or especially useful when we join tables with themselves. So we'll see an example of that today. We saw that we can specify the items, the columns that we want, or specify that we want all of them. We saw that an examples of retrieving certain fields from a particular table. Up to this point, we've been working with single tables and retrieving all the records in that table. Okay, later on, when we introduce the where clause or joins, we will talk about on how to filter so that you only get a subset of those records. We talked about distinct as well. We talked about different types that the fields could be, right? They could either be strings as varchar or integers, weights. We talked about a whole bunch of functional libraries that different vendors provide to manipulate strings, such as converting them into lower strings, upper strings, trimming them, character length, substring, concatenating the two strings, or comparing those strings against regular expressions. We also spent a couple slides on how is it that we can compare strings against a pattern, right? So that we can see if a particular string falls within a particular set of circumstances. We saw some commands for the like. We also looked at dates, and we saw that different vendors provide different operations for dates and different formats that are supported, and that depending on which version or which vendor you're going to be using, you should familiarize yourself with the documentation from them. Most of them provide a constant that allows us to retrieve the current date and also extract different portions of a date for the month, the day, the year. It allows us to also to have some simple date arithmetic, where we can add a date plus a day or month or year or a week. We can subtract dates and get like an interval on how many days, month, and years are between two particular dates. All sorts of formats are supported, and all sorts of functions. Different vendors provide different functions. Again, refer to the reference for those vendors. We saw that SQL Server provides all sorts of formats for displaying it in military format or European format, or all sorts of ones that are useful for different business, for different industries. We then focused on the select statement and saw how we can manipulate the data as we read the data. Remember, this is all reading data that has already been inserted in the database, right? As we extract it from the database, we can tweak it, we can massage it, we can transform the data as it's being read from the records in the table, and then concatenate something to a particular string, do some substrings, do some manipulation on string dates and whatnot, right? In this case, we saw some examples of, as we're reading records from the student table, right? We're going to generate new data based on the create new fields, calculated fields based on the values that are in the actual table, right? So here we are calculating an offset from the real year, offsetting it by 1,863 years, right, to calculate what graduation year you are. And we saw that we can start off with a blank simple select statement that is retrieving 3 fields, but then we can transform them by either concatenating to one of the fields, or doing some arithmetic expression that allows us to calculate a particular virtual field on the fly. Again, this is only for display purposes, right? It's not like we're modifying any data in the original table. This is only when it's coming out and we want to display it for consumption, generating some kind of report or something that's useful for us to analyze. We'll look at some very sophisticated ways of calculating the value of a field using these logical operators, where we can do case. Let's see. Can you please explain the double bar operator? Yeah. So the double bar operator here, right? It's basically a concatenation. It's concatenating whatever's on the left-hand side with the right-hand side and giving you the results. So the result of generating this field is going to be the concatenation of these two strings, where you have this hard-coded string concatenated by this value, which is being read in from one of the records, as you iterate over the records. So yeah, it's a concatenation operator. So the case allowed you to do all sorts of if else statements that could be used to calculate the fields based on some conditions, where each when case can have independent condition, right, which is a key more towards the if else, where each if can have its own Boolean operator. Here's an example where we have, if each when clause having its own predicate, doing its own comparison, right, and then evaluating to, depending on which one of those cases is true, and each one generating a different result based on the values of some other field A that is being used for in the Boolean expression. There's also a much more compact and easier version where the when clauses don't use individual Boolean expressions, right? It's just more like the switch case where you have some kind of constant, some expression that is compared against multiple constants, and depending on that constants, that one gets evaluated, and that's the result of the case. There's a much more compact version. Where is it? Oh, we then looked at an example on how to use this to calculate whether a student was an alumni that had graduated or was still in school. We first calculated a select statement that calculated how far you are in years from graduating, right? Which is the difference between your graduation year and the current date. Okay, and extracting the year portion of that, and then storing that result in an intermediate result set, right? And then we use that result set to further do some post-processing and use the case, right, to compare the how many years are you off from being graduating. If it was positive, that means that the current year is larger than the year of graduation, meaning that you're an alumni, right? You've graduated already, right? Alumni. Otherwise, right, if it's not positive, meaning that the current year is higher, it's smaller than your graduation year, that means you get a negative value, means that your graduation year is in the future, so that means that you're still in school, right? So just an example on how to do that. Obviously, there's also a much more compact version of that with the if statement. And again, all this, we're just reviewing what we covered on Tuesday, right? So all this should be just review. We looked at the from clause that up to this point, it was only considering one single table, right? Up to this point, all our queries were considering just a single table, right? It was just retrieving data from the one table. To make this a little more interesting, we're revisiting the from clause where we're considering now more than just one table. So here we have from two tables, the student table and the department table. And this translates to a product, right? A cross product where the results that this is going to generate are just going to be all the possible combinations, right, from both tables. Okay, so for instance, if you have 9 students and you have 3 departments, then you'll get all the combinations of the 9 students combined with all 3 departments, and that turns out to be 27 different combinations, of which many of them make no sense, right? Only 9 combinations really make sense out of those 27. Okay, if we know that one student can only be enrolled in one department, then bringing in data from one student and the department that they enrolled in, that combination makes sense. But bringing in combinations where you bring a student and then data from a department where they are not enrolled, okay, that makes no sense, right? Why would you even consider that relationship? There is no relationship, okay? Nevertheless, right, when you just say that I want data from these 2 tables and that's it, okay, then what you get is all the combinations from all the records, right, irrespective whether they're related or not, okay? And that's what we refer to as a product, right? It's a cross product of both sets. You get all the various combinations, okay? We also mentioned that if the 2 tables have the same name, right, meaning you're maybe doing a self join, maybe comparing, who's a manager, what employee is a manager of what other employees, meaning the relationships are not one table related to another table, but the relationship goes from one table to records in the same table, okay, like here, employee, then you have to give them separate names. Otherwise, it's ambiguous when you're going to retrieve data from one or the other. Okay, we'll come back to that as an example in a bit. Before we do that, let's talk about joining. Right, we said that we were grabbing information, all the possible combinations from two tables, which many of them make no sense. Right, if we have again 9 students and three departments, we would get 27 combinations, of which only 9 of the 27 make sense. Right, there are 9 students; they can only be in 9 departments, and that's it. Okay. So how do you filter out and say, well, I don't want all those other combinations that make no sense, right? All the other 18 combinations that you gave me. Well, that's where we bring in the join, right? We bring in the join and say, and we're going to filter only the ones that make sense, only the ones where we know that a student has a foreign key and it's related to a department ID by its primary key, right? And the way we do that is by using the join keyword, right? Which is basically the join is as we saw in relational algebra, is a combination of doing a cross product first, combining all the 27 choices, and then filtering out only the ones that you really care about, which gives you the 9, right? So this 9 here comes from having considered all 27, okay? And then just filtering out the ones you really care about, right? So yeah, so the join, as we saw earlier, there's the syntax is table 1 join, right? And then on the predicate, that is going to filter and only retrieve the ones you really care about, right? And we saw that there are, oops, sorry about that. Case from. We saw that there are 3 versions of this. The inner join, which is the most common one, also sometimes referred to as the natural join. So the natural join is the one we're going to be using most of the time, right? Which is basically, filter out those combinations of which one foreign key in one table is referring to a primary key in the other table. Okay, those are the only ones we really care, right? And that's the most common one. We call it just join, or sometimes inner join or natural join. Right? But we still saw that there are a couple more. You have the left join, you have the right join, and you have the full outer join. Okay, and we saw examples of that. So first we looked at the plain all inner join, where we matched these 4 orders with 2 of the Garcia and Boone, because we saw that this person ID is related to this Garcia of here, and this person ID 1 is related to this Boone, but nobody seems to be related to Dole over here. Okay. And the way we implemented that was with a simple join, person join orders, right, on this primary key, foreign key, right, and retrieves what you expect. We saw that in the left join, it was basically the natural join, plus it brought in the records from the table on the left, right? In this case, is table 1 on the left, of the records that did not meet, right? That don't have any relationship. And one might say, well, why do you even care about those records that have no relationship, right? What's the point in that? Why would I want them? And we just showed you an example, right? That where here we did the left join, right? We brought here Bob Dole. No one wants Bob Dole, right? And nevertheless, it brought in those records nevertheless, right? And we see that there was no order for Bob Dole, right? But nevertheless, the left join brought in that missing person that was not that had no reference. Now, why would you do that, right? We saw an example, right, of universities sending out invites for staff and spouse, and presumably the what we wanted to implement was, hey, send an invitation to all the staff and their spouse, if any, right? If they are married. If they're not married, I still want to give them an invite, right? So a simple natural join or inner join would not do, right? Because this one would only retrieve the records for which a staff and a spouse are related, right? But if there is no spouse, then I would not retrieve know the relationship between the two tables, right? So that would not work because I would only get the staff member that are. All right, let me repeat that. Looks like I cut out the. So I was mentioning that right, to implement this, it would not be enough to just do an inner join or natural join or simple join, because you would only retrieve information about the staff that are married, right? But if there was no relationship, then you would miss out on those staff that were not married, right? So the inner join was not enough. That you had to add a left join so that you would retrieve records about the staff members that are not married, right? Even and they had no relationship to any spouse. You want those as well, and for that you need the left join. Right? We saw that right join is basically the same thing, but you are retrieving information from the right table. Eric, did you raise your hand?
Yeah, you just cut out earlier.
Earlier, as in when I was repeating myself with the inner join, or did I cut out again?
You cut out on the left join, I think. Someone posted in the chat too. Alyssa posted in the chat.
Right, and I repeated myself because of that. Did I miss something, or did you want me to go over something?
Oh, never mind then.
All right, thank you. Yeah, please let me know. All right. Yeah, so right join is basically the same thing as the left join, right? But we're grabbing information from the right table. And the example that we had here from our example of persons and orders was that we're grabbing all the orders, even though there was no relationship to persons, right? It's empty on the right, on the left, sorry. Okay, full join is basically doing a first retrieving all the records that have relationships, and then filling in below that, the joins from the left and then joins from the right that have no relationship between the two tables. So again, going back to the example of the orders and the persons, right? We end up with first the ones that are related, and then the ones that are not related from the left, and ones that are not related from the right. Okay. Okay, so let's now segue into something new. Now, we've only taken into account joining two tables, right? So here we're joining person and order, right? And that's pretty simple, right? You just say, person join order on. Okay, so that's the syntax. Now, what if we want to join 3 tables or 4 tables? Well, this syntax could get out of hand really quick. Okay, basically here's our first join, joining the student table and the enrollment table, and it's fairly simple, straightforward. So where you are saying student join with enrollment and that predicate. Now, what if you want to join the result of that? You want to join it with another table, because the enrollment table has a foreign key to the student, and that the enrollment table has a foreign key to the section, right? So you can navigate between student to enrollment, and then from enrollment to section. You can make all those equal, right? The student ID is equal to the enrollment student ID, but then the enrollment section is equal to the sections ID as well. So how do you join all those 3 together? Well, you would have to first put in parentheses what you've already joined, right? And the result of that would be the input of another join. So this would be another join. So join that with the section, and then on the fields of the inner table section, the enrollment with the section. So this syntax is can get ugly very, very quickly, right? So I want to introduce to you another alternative syntax, right? Which as follows, right? So you have the ugly syntax, right? Well, this one's not too ugly, right? We're doing an inner join of an employee with department. That's easy enough. predicate. Yes? Okay, that's simple, right? Because we're joining two tables. Well, here is the same exact two-table join, but written in this other syntax, where you say select star from, and in the from, you just do the cross product syntax, right? You say it's from employee.
You cut out again, Professor. Sorry.
Okay. Thank you, thank you. Yeah, I was saying that this syntax is fairly straightforward to read, right? We have the normal join syntax where we are joining the employee table with the department table on a given predicate, right? The department ID of both the employee and the department. That's not too hard to read, right? But now I wanted to introduce you an alternative equivalent syntax where we are doing the cross product, right? We have the cross product of employee and department. And so you just list the tables. That's all you do, right? You don't join anything on anything, right? And instead, you put the predicate, instead of putting it after the on, you put it after the where, okay? Now, what does this buy you, right? This syntax, what it buys you is that if it's just two tables, it's almost identical. You know, it doesn't really matter if it's just two tables. But if it's three tables or four or five, right? If it's more than just two tables, this syntax is very much easier to read than this syntax, because this syntax doesn't require parentheses or things that are nested one side of another, whereas this syntax requires a whole bunch of parentheses, right? So this is a great segue into the where clause. What the heck is this where clause? Let's talk about the where clause. Okay. Okay, so the where clause of a select from where basically allows you to list in the from clause all the tables that you want to consider. And this will do the cross product, right? We'll consider all the combinations of all the records with all the other records in different tables. And what the where clause is going to let you do is provide all the predicates, right, by which all those combinations are going to be filtered out, right, including predicates that consider the foreign key primary key relationships between the tables, right, predicates that do the join, plus predicates that are not necessarily key, right? They're not primary key, foreign key, are just predicates based on the other fields. You know, maybe the salary, right? You know, I want the folks between salaries between $70,000 and $80,000, right? That's not primary key, foreign key predicate. So the where clause allows you to combine, right, predicates that filter by relationship, primary key, foreign key, and allow you to filter by any other non-key field values. All right, let's look at examples. So here you're going to have a whole bunch of Boolean expressions, right? You know, this has to be true, and this has to be true, and this has to be true, or this has to be true, and not something. So you can use a combination of and, or, and not, right? And the parentheses of Boolean expressions to filter exactly and pinpoint exactly the records that you care about. Okay, so here they are. These are some of the operators that are useful to create these Boolean expressions. Okay, you have the equal operator, obviously. You have the not operator. Careful, it's not bang equal. Right, it's not bang equal, so it's not that. Right, so I'm gonna scratch that. I'm gonna say it is not that. So I'm gonna do a strike through. Okay, so you can't do that. And there was another one. Okay, yeah, it's not the equal. It's not equal like in other languages. Right, so I'm gonna do a strike through here as well. So it's not that either. Okay, that's I don't think you could understand that. Not double equal. Equal. Not and bang equal. Okay, so just to remind you not to use syntax that you might be familiar in other languages. Okay, not bang equal. Okay, careful with that. So yeah, so you get all the comparison operators that you have come to be familiar and love in other programming languages. They're available here as well. You know, greater than, less than, greater than or equal to. Plus, you get these other operators that allow you to work with ranges, right? Whether a particular value is within a particular range, you know, using between. And like allows you to do some pattern matching, right? Whether a string is within a particular regular expression, or in, you know, whether a value is within an array of acceptable possible values, right? So there's these other operators as well that you can use for your Boolean expressions. So here's a couple of really simple examples. You know, given this particular table, right, we can filter out and give the results of retrieving those records whose city, right, is equal to Lowell. Okay, so it gives you those two records. Here's an example of using and to combine combine two predicates, right? We have the first name equal Bob and last name equal Dole, right? So those are two predicates that we're combining into one super predicate, right? Into one big predicate with combining it with the and operator. You use or as well, right? Again, to combine these two. Or you can, you know, do some fairly complex Boolean expression, combining and or and using parentheses, you know, which is very common Boolean algebra. Yes, that you should be familiar with. Okay, so let's go back to the fact that we were saying that we wanted to use to write joins that might be fairly complex, right? That might be joining not just two tables, but might be joining 3, 4, 5 tables, right? So let's talk about that on how you would do it using the where clause. We already gave you a hint, but also we want to consider that not only are we going to have the where clause with joining, right, with joining tables, but also predicates that consider non-key fields, right, like, you know, graduation year or somebody's salary or somebody's birthday, right? Those are non-key fields. Those are not primary key and foreign key. So the where clause, you can have both, a combination of foreign key, primary key combined with non-key fields. So let's take a look at this. So here's an example on using the where clause to just do filtering based on non-key graduation year. That's not a foreign key, it's not a primary key, right? It says I want those students that are either graduated in 2005 or graduated in 2006. Perfect, okay? Or here's an example where we are joining 3 tables, right? To join 3 tables using the join on. Notice how complex and hard to read this is, right? We're saying, okay, we want to join the student and the enrollment on this primary key, foreign key, and that result, we want to join it with the section on that foreign key to primary key. Yes? So that's pretty hard to read. Whereas this one down here is an equivalence query that is grabbing from students S, E, and K, right? Those tables, student, enrollment, and section. And here's where the joining happens, right? I don't want, you know, depending on how many records you have, this could be hundreds of result sets, right? You know, combining these students with all the enrollments, with all the sections, it could be pretty big. It's the cross product of these 3 tables. It could be, you know, hundreds of combinations. But we don't want all the combinations. We only want the combinations where the student is somehow related to some enrollment. And then those enrollments, right, are somehow related to some sections. See that? Right? So basically, you just have to use the foreign keys and primary keys, right? Make them equal to each other to filter out right? All the ones that have no relationships, and only keep those records that are actually related to each other, right? Where some student is enrolled to an enrollment, and then that enrollment is somehow related to some sections, right? So this syntax is so much easier to read, right? Now, this syntax here, we call it the explicit join, right? And it's explicit because we are explicitly using the keyword join, right? Whereas down here, we're not explicitly using the keyword join, but you get the same behavior as if you were using the keyword join. So it's basically the same operation, but using it by what we call an implicit. It's implicit join as opposed to an explicit join. Okay. And as we said earlier, the where clause can house both types of predicates, right? Those predicates that are for relationships, foreign key, primary key, together with relationship with data, whether they match a particular value, right? Non-key predicates. It should always be primary key equal foreign key. Yes. Well, the order doesn't matter. It could be foreign key equal to primary key. The order doesn't matter. But when you are joining two, the question is, it should always be where primary key is equal to foreign key. And yes, to do the join, right? This is exactly what we're doing, right? We're saying this primary key is equal to this foreign key. And we're saying that this foreign key is equal to this primary key. So the order, whether it's primary key, foreign key, doesn't matter, right? Yeah. It's later on we'll say right that the relationships in relational databases is bidirectional, right? And basically that you can navigate from one table, one record to another record. As long as the primary key and the foreign key are equal to each other, you can navigate from one record to the other. Okay, you can navigate from the user, or a student, to the enrollment, because the primary key of the student is equal to the foreign key of the enrollment, or from the enrollment you can navigate to the student, right? Vice versa.
Hi, it's so primary key first and then foreign key for the other slot. That would be best practice, right? Because I noticed a lot of slides
for reading, yes, it's easier to go from small context, right, to wider context, right? Say, from like one to many. It's easier to read if you put first the primary key of the one, and then you put the foreign key of the many.
Okay,
so yes,
thank you.
It's easier to read, but for implementation, it doesn't matter. And later on, as I said earlier, right, we'll come back to this and say that in relational databases, these relationships are bidirectional. You can navigate when a primary key and foreign key are the same. It allows you to navigate between one and the other. Whereas we're going to see that when we try to map these data models, these relational data models, meaning data models that are implemented based on relational databases, when you try to map that to object-oriented data models, like class diagrams and Java classes and C# classes, those by default are not bidirectional, right? Because typically a class, the way you implement a one-to-many relationship in C# or Java is you use arrays, right? Which you don't have in SQL, right? So a student that has many sections, the way you would implement that is perhaps having a user having an array of sections, right? And typically that relationship is in one direction, right? The student has references to an array of sections, so you could visit all the sections just by iterating in a for loop. But normally, typically in the data model, the sections don't have a pointer back to the students that they belong to, right? So you can navigate down to the section, but once you're in the section, you can't back up to the So even though in relational databases, they're bidirectional, when you map them to other data models, they're not. Okay, so yeah, we'll point that out a little later. Getting ahead of myself.
You cut out again just at the end there. I'm so sorry.
Oh yeah, no, not at all. Yeah, I need to solve this. What's going on? Yeah, no, I was only mentioning, I was getting ahead of myself, saying how the mapping of these relational databases, right, doesn't always map one-to-one with other data models, such as object-oriented data models. But we'll get a chance to play around with that a little later in the course. Yeah, so between allows you to do comparisons or write Boolean expressions based on ranges of values, right? Where you can say, hey, I want the records where the value of this field is within this particular range, right? Value 1 and value 2, and those values could be a numeric, right? Or they could be also strings, right? And numerical makes sense, right? You go from small value to bigger value. String values or varchar, they would be by lexicographical or dictionary order, right? So here's an example where we are retrieving all the records of where the last name is anywhere between Boone and Garcia, right? So that would come back with Boone. Whereas you can do the inverse, right? Where you can use the not operator, which inverts the Boolean result, right? So wherever it's true, it becomes false, false becomes true, right? So this one returns all the records that are not between Boone and Garcia, which is basically the inverse result. You can also use the in operator, which takes the value of a column and then it compares it against all the values within the in, which is an array of possible values that are valid values for that particular column. And what it does is just starts iterating over those values. And the first one that it finds, right, it stops iterating. It says, oh, I find a value, I'm done. I don't have to iterate for the entire list in the in array. So here's an example where we're checking to see whether the last name is in, and then you have Boone and Garcia. And if it finds it, then it returns the record that meets that criteria. So these two records, right, are filters from these three records over here. Obviously, you can also call on the where clause. You can call other functions that can compute a value based on parameters, and then the result of those functions can be used as for comparison purposes. Right here, we are using the extract, right? That is taking the current date and retrieving only the year. Although you can write your own functions. We'll see later on when we do programming the database, right? We'll create our own functions, and you can call these functions to compute something that can then be used here in the where clause. Also, current user is available. The base, whoever logs in, you can then use that in your logic, right? So that one query for me when I'm logged in comes out to be with some other results if someone else is logged in. All right, let's talk about subqueries. Any questions? All right.
I have a quick question.
Yes.
So in slide number 77, it says select everything from person where last name between Bones and Garcia. Wouldn't that be the second result?
Boone, between Boone and Garcia.
I return Boone instead. So
yeah, it's returning Boone.
Would it be Dole? Sorry, I don't.
Oh, between Boone and Garcia. Actually, I think we would need to add Dole in here as well. So it would be Boone and Dole. Yeah, no, I would add here as well.
You
Because
cut
dole
out
is
again,
between
Professor.
AC. Yeah, I know that dole would also be part of that result.
Why is boon part of the result then, if it's between the two of them?
A, B, so lexicographical, so anywhere that's between A, B, C, D, E, F, G. So B is in there, D, so any C would be in there, D would be in there, E would be in there, right? And so any of those values would be in there as well. Anything
So
that falls lexicographically in there.
are you saying that like even just because it starts with a B, like
Yes, in dictionary order.
but if it's boon, would things that start with BA be in it? Even though
No, anything after Boone and before Garcia.
oh, but boon is inclusive within
It's
it.
inclusive, yes. And you can also specify whether you want inclusive or not. Yes.
Got it. Okay, thank you.
So Garcia isn't inclusive.
It's not inclusive. No, it's less than Garcia. Yep.
Cool. Thank you.
Yep. All right, so let's talk about subqueries. So a subquery is a mechanism that allows you to take the output of one query and use it as an input into another query, right? So it allows you to create a flow of data, right, where you can do progressive filtering, right, where you identify a large chunk of data that you can then feed that into another filter, and then reduce that large chunk of data to something smaller and smaller until it allows you to identify exactly the piece of data that you want. Okay, as opposed to, I mean, you don't need a nested query. You could put it in one big query and put lots of ands and ors and nots and come up with a really good Boolean expression that allows you to identify exactly what you want. But sometimes it's easier, right, to break up one large query into smaller queries where one of them first identifies a subset of the data, and that gets fed into another query that does additional processing, right, and filter some more. And so these subsequently, right, come up with the actual result at the end, right? So let's take a look at some examples where, for instance, the syntax is as follows, right? Here you have an outer. Oh, before we get into it, the nested queries can be used in anywhere in the different clauses, right? You can put it in the where clause, you can put it in the from clause, and you put it in the select clause, right? But you can put it in all three of them, right? There are some restrictions depending on whether you use it on where, from, and select. Basically they, because these clauses expect certain pieces of information to be formatted in a particular way, right? So let's first take a look at the where clause, right, of using subqueries here, from, and then select. So let's look at the where clause. Right, so the where clause, right, allows you to have a nested loop. Here's a nested query. There it is, right? And notice what we're doing, right? We're saying where, and then we're going to compare this field from some table 1. We're going to compare that field 1, and we're going to we're asking, is the value of field 1 in this here? So what is that? Well, in, right, the operator in, basically what it does is that it iterates, right, checking to see, right, if this value is in some array or collection of values, right? So the in operator expects the right-hand side to come back with a set of individual values, right? So, as in value 1, comma, value 2, comma, value 3, and so on and so forth, okay? So this select statement better come back with what the in operator expects, right? So here we have this inner select, notice, right? It's saying from table 2, I'm extracting field 2 is equal to value 2. So actually this comes back with what? With a single value, one single value, right? So this could be maybe greater than value 2, like that. Then that means that this would come back with a multiple values, right? All the values where field 2 is bigger than value 2, right? So it could be many values, yes? And that's perfectly fine, right? This comes back with multiple values, and whatever that comes back, this is going to be compared against all those values. Make sense? Okay. So let's look at an example, right? An example might be, imagine we had, we were selecting the first and last names or whatever, right, from students where the first name is in Alice, Bob, and Charlie. So one of the problems in this query is that Alice, Bob, and Charlie is a hard-coded list of folks, right? Presumably they are first names of some students that actually exist in this database. But somebody might ask, well, why those three? Right? What if Charlie graduates, right, and moves on? Would I have to come back here and update this list? Right? Maybe this was not a good design, right? Somebody might ask, well, what is the criteria by which you chose these three folks? So one might say, oh, yeah, I can write this a little better and say that those three students, the criteria is that they were all in the science subject, right? They're all science students. Okay, so now I can rewrite this. Let's make this red. And I can rewrite this hard-coded list of students into a more generic list where I'm extracting only the first name from the students where the subject is science. See that? And so now the first name is going to be compared against 3, 4, 5, whatever students are actually in the science department. Make sense? Now, it would be a mistake to extract more than one thing from this query, okay? Because remember, first name is going to be compared against individual values returned from the select statement. So it would make no sense for me to extract more than one value, right, as I retrieve the students, the science students, right? So yeah, it would be an error for me to add more fields here, okay? If I add more fields here, I would not be returning a list of values. I would be returning a list of records, right? A list of rows where each row might have multiple columns. That's not what the in operator is expecting. The in operator is not expecting rows with columns. It's expecting just an array of individual values, right? So yeah, so you would not do this, okay? That's why it's crossed out. So here's another example. So imagine we had a list of many countries, right, all the way through Russia, right, and so on and so forth. Okay, with all sorts of statistics and whatnot. Okay, so somebody might ask, hey, somebody might ask the following query. Give me all the countries whose population is larger than Russia. Okay, so there are a couple of things that need to happen here, right? I need to be able to first, right, calculate the population of Russia. I first need to know what that is so that I can then filter the queries, the countries that have a population greater than Russia, right? Because I need to convert this into list of countries with population greater than, and then a single value, right? So this needs to be converted into a single value, right? So how do I do that? Well, the outer one should be something like, select name from some table where the population is greater than what? The population of Russia. So I need to calculate what is the population of Russia, right? So it could be just, select population from some table where the name of the country is Russia. And that gives me a single value. Notice that this is a greater than operation. operator. See, that operator means that I need to calculate one single value against another single value. It would make no sense that the right-hand side would give me a list of values. Or even worse, it would make no sense for this to be a list of rows with a whole bunch of columns, right? So I have to make sure that I compare things correctly with other things, right? So I need to make sure that this indeed evaluates to a single value so I can do the comparison. Make sense? Right? So yeah, so the where clause, using subqueries in the where clause have to either evaluate to a single value like this, or evaluate it to an array of values that can be used in the in clause, right? In the in operator. But never, we don't want ever to evaluate into a set of records with rows and columns, right? So in the where clause, we don't want that. It is, but instead in the from, when we use it in the from clause, we do want rows and columns, okay? So let's take a look at that. All right, so in the from clause, like here's a nested select statement. There it is. Right, there's an inner select statement. This is expecting, right, just like the from clause, you have suppliers is a table, right? And that table is indeed a whole bunch of rows and a whole bunch of columns. Yes. So the from clause does expect, right, all of its arguments to be in the format of rows and columns. So here's my first table with rows and columns. And here, right, this also needs to be in the format of rows and columns. Okay, so let's take a look at the rows and columns. So this select statement is retrieving two fields. Here's one of them, and here's the other one. Right, one of them is just a field, a normal field. The other one is an aggregation, right? Some aggregate, whatever, right? From some table. So this is returning indeed two columns from the orders table, right? And it's filtering it and grouping and doing whatever, right? So this is the second table, right? It looks like a table. Right? So this is my first table, and this is my second. Sometimes this is referred to as like a virtual table, right? Or we call it an inline view. An inline view, that's also a very common name, right? We give it a name. There's subquery 1, right? Because otherwise, now the name of this table is clear, right? The name of the table is just called suppliers. But what about this thing that it looks, it's generating something that looks like a table, but it doesn't have a name because it's not a real table. So we give it a name. We know how to do that, right? With the, whenever, we learned earlier that you can give tables there, you can rename them, you can give them names here locally. And that's exactly what we've done here, right? We've given the table a name called a subquery 1. Once you give it a name, you can treat it as if it were just any other table, just like suppliers, right? Is a table, this first table, and it has its own fields. Well, subquery 1 can also be treated like any other table with whatever fields are inside, right? Remember, this table is generated with this data, which has a whole bunch of records, right? Which have these columns, supplier ID and total amount, right? Which I'm using to join the two, right? I'm using them to join these two and to filter out where the suppliers and the subquery 1 match. And here I'm extracting fields from both, either the supplier and the subquery, the name from the suppliers and total amount, right, from the subquery, right? So you can treat it as if it were just a normal table, okay, which is pretty cool, right? So yeah, so you can have it in the where clause. You can have subqueries in the where clause. You can have subqueries in the from clause. We call them inline views. And you can have it in the select clause as well, right? So here's another select statement, right? Embedded in the select. Here's a select, right? That has one field, has two fields, and a third field, which we're going to call subquery 2. Okay, So at the end, you're going to have 3 columns. The first column is going to be called owner. The second column is going to be called table name. And the third column is going to be called subquery 2, right? We name it using the as keyword, as, right? And which values for the owner? Well, whatever values are in the tables table, right? The owner field in the tables, right? And what's this column? The values for table name? Well, whatever values are, table name values are in the tables table, right? What are the values for subquery 2? Well, whatever this evaluates to. Now, this needs to evaluate to a single value. It cannot evaluate to a list of values. It cannot evaluate to records with columns and rows, right? It has to evaluate to a single value, okay? So again, some limitations on what we expect nested select statements, right, to be in these, depending on whether it's in the where clause, in the where clause, in the from clause, or the select clause. Okay. All right. So let's talk about unions. So unions are, like the name suggests, right, is it's going to allow us to do a query, and it comes back with a whole bunch of rows and columns, right? And do another query with a whole bunch of rows and columns. And union allows us to take the results from both results and then combine them into a single one, right? And have the results of the first query, go first, and then the results of the second query, and just concatenate both of them into one single result. Okay. Now, for this to work, right? Like for instance, here it is, right? So here's one select statement that is retrieving some column names from table 1, and then another select statement which is retrieving some other columns from some other table, right? Now, for this to work, right? Imagine, right, that if you have some columns here and you have columns over there, well, if this one comes back with columns A, B, and this one comes back with columns C, D, then the union here, the union keyword, which goes between the two queries, right, is going to have a hard time saying, well, which ones, how do I concatenate those, right? How is A related to D, right? Is B related to C? I mean, what columns go under which columns, right? So for this to work, the names of the columns have to match, right? So if the first query comes back with columns AB, well, the second query also needs to come back with AB, and then it will know that the results, they match, right? The A column goes under the A column, right? And B goes under B, for them to concatenate. Also, the data types need to match, right? If A over here is an integer and A over here is a string, then that's also going to have a hard time creating, right, one single result, right? So the data types need to match, the names of the fields need to match, right? So yeah, so we need to massage, right? We need to massage the results of the tables, right, of these results, to make sure that they match so that the union works. Okay, so let's take an easy example here, right? So say you have, two tables, right? One that represents employees in Canada, and the other one represents employees in the United States, right? And say you want to do a union between the two, okay? But it turns out that the employee names on the employee Canada table calls them E names, and the employee USA table calls them EMP name, right? Even though they're the same data type, right? And we know that logically the data stored means the same thing, right? The database doesn't know this, right? The database just does what it's told, right? So it doesn't know that E name is an alias for EMP name, right? So if we want to do the union, we're going to have to explicitly rename these fields so that they match before we do the union, right? We also should check to see if the data types match as well, right? If they don't match, then it's not going to work, right? So here's an example where we are joining or creating the union of the employees Canada with the employees USA, right? But we know that the column from the Canada table, it calls the employees E name, but the ones in the USA, they're called EMP name. So what we're doing here is that we are renaming the column in the USA table to have the same name as the one from Canada, so that at the end you end up with just E name, okay, as a result, and they go under the same column. Yes. Now notice that before we did this, right? Notice that we had an employee that, right, maybe at some point worked in the Canada office, and hence has since then moved over to USA, right? And so when we do the union, it would be showing the same Dole Stephen, right, twice in the resulting union. So by default, the union is going to remove any duplicates, right? So if Dole Stephen appears twice, it'll remove the duplicates, right? But sometimes it's useful to bring in both of them, right? And so you would have to explicitly tell the union to do union all, bring them all over, right? I want everything. Don't skip over any duplicates, okay? All right, so let's take a look at the order by. So order by is a operation on the resulting data that's coming out from the database for us to be able to sort or reorder the results as they are displayed to the user, right? So order by doesn't actually sort the data in the database. It leaves the original tables all alone, right? It doesn't touch them, right? For the table's point of view, order doesn't really matter, right? The tables are treated as mathematical sets, right? So in set theory, right, there is no first element or second or third, right? There's no order whatsoever. Here, the order is only meaningful when it's being displayed to the end user, right? I want to reorder, right, the records when they're being displayed to you, because we might want to look at the data sorted by date, or ordered by salary, or ordered by whatever, right? And by phone number, by last name, okay? And so only for human consumption, visual consumption, because it's convenient to see the data sorted in a specific way, right? But it doesn't actually reorder anything in the original tables, right? And so the syntax is to order by and column name, or you can have many columns separated by commas, and then configure whether you want it to be ascending or descending. By default, it's ascending, right? And if you say order by last name, right, then you'll get all the results ordered by last name ascending. Okay, but you can have order by last name ascending, comma, salary descending, right? And then it'll sort first by last name and then sort by salary second. Okay, if you have the same last name. So here's a couple examples. We're ordering by last name persons, right? So it's sorting this Boone, Dole, and Garcia so that it's ordered by last name, the results, okay, or descending. Self joins. So self joins, if you remember, we had a we had in our class diagrams, we had some classes, or I think we had at least one class that had a self join, right? And what by a self join means is that it's a data structure that allows us to create hierarchical recursive data structures, right? Where records or instances of the same type, right, are referencing each other so that it allows you to create these hierarchical structures like a tree, where you have a kind of like a root at the top, right? That then has a parent-child relationship. So the parent and then has many children, and then each child can have many children, and then each one of those have many children, right? Where you can navigate from the root down to the children, and from children back up to the parents, right? So to create these data structures, they're useful maybe for establishing relationships of items in the same table or in the same class, right? So for instance, you might have employees, right, in an employee table. And even though in a company, everybody's an employee, right, you can have a hierarchy of employees, right? You can have, individual contributors, right, that have no managerial responsibilities, right? I just come in to work and nobody reports to me, but I report to my manager, and my manager reports to their manager, right? And that manager reports to the director, and the director reports to the vice president, and the vice president reports to the president, and then to the CEO or whatever, right? So you have this this hierarchy of, somebody at the top and then everybody reporting. Here's another example of categories, right, where you might have a top level category that has many subcategories, and then in each one of those categories has a subcategory, and each one of those has subcategories. So let's take a look at this category, right? And the way it's implemented is that, you have a primary key ID, right? Primary key, which is auto incremented, and then you have the name of the category. There it is, right? Then each category can have a pointer to other categories as being their parent category, right? So they will be implemented as foreign keys, right? That reference other records in the same table with some primary key. Okay, so this one allows you to, again, create a hierarchy of categories, and the data would be implemented as follows. You insert maybe some top level category, and maybe just call it top. Notice all these nulls here. This means that these are all the primary keys, which we're saying null because they are auto incremented, right? So they're given automatic numbers, right? So this first one gets inserted with a primary key of 1. Also notice that the name is top, and it has no parent, right? So it's at the top. So nobody is its parent. The root, it's at the root, right? Then, because this is the ID is 1, the top is 1, we're inserting 2 subcategories. One is electronics, and the other one is movies, right? Which are saying that the parent ID is 1, which is the ID of the top one. Yes, because it was inserted as the first one, right? So these are 2 subcategories of the top one. And then the IDs for each one of these is 2 and 3. So this is 1, this is 2, and this is 3. Okay, I guess it'd be useful, right, if I make this, there we go. Okay, so this would presumably be the IDs of each one of them. So yeah, so this says this is 2 and this is 3. So PCs, right, or personal computers would have as parent the electronics, number 2, whereas DVDs and Blu-rays would be under movies, which is ID number 3. So the parent is number 3. Okay. Now, once you have inserted this data in this hierarchy of data, you can then start making queries, as in, okay, well, give me all the records that are related to one another. Okay, where you're going to try and relate records in some parts of the table related to other records in some other parts of the table, right? Typically, you relate one table with other tables, right? Here, you're relating one table with itself, right? Normally, you think of, I'm going to relate these records in this table with the records in some other table. Well, here, the parents and the child both live in the same table, right? So when you're going to join tables, you have to list both tables that you want to join. But in this case, both tables are the same table categories. So you have to definitely you have to provide a different name for each one of these tables so that you can differentiate the child versus the parent. Okay, so here we're giving a name to the categories tables, child and his parent. Okay, you just cut out. Yeah, let me repeat that. Right, so here we're trying to join, right, just like we do join any two tables, right? Usually you have a relationship between one table that you want to join with another table. So it usually is you list both tables, table 1 and table 2, and then you join saying that the foreign key of table 1 is equal to some primary key of table 2. But in this case, right, the records live in the same table, not in separate tables, right? So here we're listing the, quote unquote, two tables, but it's really one table, the same table categories, but we differentiate them by giving them separate names, child and parent, okay? And we're extracting the child name. And then we do the join, here's a join, where we're joining, right, the foreign key in the child table with the primary key of the parent table. See that? Right? Again, if these were two tables, it would make more sense, right? It would be the foreign key of table 1, right, pointing to the primary key of table 2. But now table 1 and table 2 are really the same table. Our records are different records that live in the same table, and the only way to differentiate them is to give them separate names. Okay? So yeah, so this gives you a hierarchical representation and outputs, all the child and parent information, right? So yeah, so self joins. Then let's look at portable enums, right? So portable enums are we saw when we were looking at class diagrams, right? We were looking to represent certain data types that had a specific set of valid values, right? And the way we implemented it was by, for instance, we had a movie class, and of which one of the fields was genre, and we wanted to limit the values of that variable and say, well, the only valid values for genre can only be these here: comedy, drama, and horror, right? It can't be anything else but those three. And so the way we implemented it was with the stereotype enumeration, right? That basically said that you should not interpret this as being a class. You should interpret it as a new data type, definitely, but not a class, where these are not properties, right? These are just a list of the values for which this variable can be only that set of values, right? So we want to implement that in relational databases too, right? And we want to implement it in such a way that it's going to be implementable in any vendor, right? Whether it's SQL Server, Oracle, Postgres, MySQL, right? And so let's look at some of the challenges. Well, the first challenge is that MySQL already provides a keyword called enum, right? And it does exactly what we need, right? We declare a variable, and we say that it's an enum data type, right? Meaning that the only possible values for name, right, is that it could possibly only be small, medium, or large. And those are the only three possible values for name, okay? And that's fine. That's exactly the feature that we want, right? The problem with this is that it's only enum, right, is a keyword that is a reserved word in MySQL. Other databases, some might have that keyword. Some databases might not have those keywords, right? So if you implement the enumeration constraint using the enum keyword, you'll be stuck. You'll be stuck with MySQL implementation. If you ever want to change and import, export this database and then import in another competing database, right? It'll fail, right? It'll say, oh, I don't know what the enum keyword is, right? So you're stuck with a specific vendor. So as much as possible, we want to avoid any keywords or any features that are specific to a specific vendor, right? So that's where comes in the idea of a portable enum, meaning I can port this implementation from one vendor to another vendor, right, without any problems? How do I implement in such a way that I can tomorrow go from MySQL to Postgres to SQL Server to Oracle, and this will still work, okay? So the way we're going to implement it is that instead of using the enum keyword, right, we are going to implement it using a dedicated table, right? We're going to create a table called genre, right, and of which we're going to have the the column name of our char, right? And we're going to declare it as a primary key, meaning it cannot repeat. Okay. Also, it's a primary key. It can participate in relationships, right? Foreign key, primary key relationships. All right. And then once we have that, we can then insert into that table and that field all the 3 possible values, right? And notice that they are unique, right? And also, this is very convenient for user interfaces. You know, we can query all these genre and populate a dropdown, right? Which is perfect, right? I can select the genre from a dropdown. You know, I can insert a new genre here, and the dropdown would update nicely. So this is a great solution like that. If it were implemented as enum, I could not do that, right? I could not query, right, for the list of the genre for population. It would be not listed anywhere, okay? Whereas here, I could query, you know, what are all the genre, and then I could just populate my user interface, right? So that's one of the benefits. And so once we've implemented the genre table and populated it, then we can create the other relationship between movie, right, and genre, which has the movie has a genre field, which is constrained. Its values are constrained by the genre enumeration, right, which can only have these values. So to implement that, we can declare a movie table, right, movies, I guess, and then the field, the field genre, the way we constrain it is that we say that it's the same data type as our valid values, but we say it's a foreign key, right? That the genre field, right, can only possibly have a reference to the name field in the genre table, right? So meaning that the values, because of referential integrity, right, the values for genre can only possibly be from the values of these primary values, primary key values, right? And that's how this would never allow me to insert here anything other than the values of these primary keys in the genre table. Make sense? Which is exactly what we want. It's behaving like an enumerated data type, right? It's not letting me do anything other than the values that are there. Okay? All right, any questions? Make sense? All right, excellent. Let's keep going. Right. So we just talked about subqueries, right? Where you can have select statements, right, inside of other select statements, right? You can have it inside the where clause, inside of the from clause, instead of the select clause, right? But in particular, one that is very, very useful and used quite often is subqueries inside of the from clause, right? Let's take a look at that real quick. Here it is, right? Here's a, no, not there. Here is a query, right, inside of a from clause. You'll notice that it's fairly hard to read, okay? I think I asked you to do one of these in the homework just to practice, okay? And no, they're fairly hard to read. I mean, you know, you have all this code inside of a larger piece of code, right? And so ideally, right, to make this simpler, it would have been nice if we could name this, right? You know, like we've done in earlier examples, we have done something like, you know, let, you know, Q27 equal some big select statement, yes? And then we can use Q27 as, you know, as a variable and put it in this from clause, right? Would be nice if we could do that. I mean, we've been talking about it for a while, but we've never actually implemented it, right? Well, until now. Look at views. So views allows us to do just that. So what views allows us to do is take a select statement and give it a name. Give it a name. Once you name that select statement, right, you can use it as a variable. Anywhere you can put a select statement, right? Whatever that returns, you can use the name and put it in the from clause, in the select clause, in the where clause, wherever that might be. Okay, this is very much like in functional programming, right? In programming languages, right? Instead of having one big main clause, main function, right, where it's thousands of lines long, right? You are instead encouraged into breaking up, something fairly complex into smaller, more manageable pieces of functions, right? Where you have maybe a handful of functions, and each one of those functions can then call other functions, right? So this is a mechanism we refer to as abstraction, right? It allows you to create something that is complex into small abstractions, each one then becoming even smaller and smaller into eventually becoming, actual native predicates. Yes. So same thing over here, right? Instead of tackling, this huge query like that, right? We would love to give this a name and maybe just call it subquery and leave it like that, right? Whatever that subquery is, right? That'd be ideal. And then now this becomes much easier to read. Obviously, you would give this variable a meaningful name, just like you give a function a meaningful name, right? And that would definitely would improve the readability of this, okay? Also, just like functions, every time you call a function, it executes brand new, right? Same thing here. These views, you give it a name, but then whenever you refer to this name, they execute brand new, right? Like the very first time that they execute. Okay, so just like you in functions, you have, you might say, well, this overhead calling functions, right? You have to create a stack, you have to populate that stack, right? And then you have to do a jump to that function. You do all your execution. Then when you come back, you have to clean up after that function, right? And so there's some overhead of using functions, obviously, right? And they execute brand new. Same thing here, right? There's some overhead, whenever you use a views, that they have to re-execute, do the whole calculation over from scratch, and then come back and then clean up after themselves once they're done. Let's see, does the subquery exist in a different SQL file? So you can import them, or do you write them in the same SQL file? Yeah, so when they get exported, they are exported in a separate file, and you import it as a separate file, just like a table, right? It gets exported one table per file. Same thing with views. But in SQL, you implement them over here. So when you open up a database, right, you have tables, and you can create these tables, and then you have views here. So just like you can create a table, right, you can create a view, okay? And when you export the database, all these tables are exported to their separate SQL files, one SQL file per table, and same thing with views, right? You can import them independently and whatnot. Okay. Yeah, right. So basically, what does this allow you to do? It's create a reusable, just like functions allow you to create a reusable algorithm, views allow you to create a reusable select statement, right? That you can refer to it by name. All right. Okay, so here's an example. We can create a view, and we give the view whatever name we want, even included, right, with spaces in between. As long as you have quotes, right, you can have spaces, right? And then that, now that I've named it, here is the actual select statement. And the select statement is doing what? It's it's looking at the products, and I only want the products that have not, right? So basically, current product lists. We might have tens of thousands of products, of which only a handful have not been discontinued. So maybe just 1,000 products, right? So this evaluates to those 1,000 products that have not been discontinued. Now that I have declared it by name, I can use it as if it were a table, as if it were an actual table. I can say select from current production list. And this is exactly equivalent as if I would have had this, right? Parentheses and the select statement, right? Some embedded select statement, right? That computes, and the output is then used as an input for the other select statement, right? But certainly this is much easier to read. So definitely this is much easier to read, right? The embedding a query inside of a query, right? And you can have subqueries defined for other subqueries, right? So for instance, here is a create view statement. So we're creating a view with its select statement, which that select statement includes another nested subquery. So you can get very fancy here, very fancy key queries, right? You can create views in terms of other views, right? So here's a view, right, that is declaring a select statement, but that select statement includes a from clause that is referring to another view, right? So you can have views to generate other views, just like you can create, just like you can write a function in terms of other functions, right? You can create this hierarchy as much as you want, right? And then out here, right, when you do select star from category sales, blah, 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 right? That resolves to this select statement. And when this select statement runs, it has to resolve this view, which is another select statement. So you have like a select statement within a select statement within another select statement. Very much like you can have a function within a function within a function, right? And obviously your level of architecting this depends on how granular you want to create this, right? How flat your design is, or how deep your design is, right? So here's an example that we've been using for quite a while, right? That we've been using this syntax to denote the idea that we were storing the results of a select statement into some kind of variable, right? And we've been using this equal, right? Q65 equal to some select statement. Now we can formally actually implement it in MySQL by using this keyword. You can say, create the view Q96 as, and then the select statement, right? Which conceptually means this, right? Then wherever you can use Q96, right? You can use it here as well, okay? And then to execute it, right? To execute it, you can just refer to Q66, right? 65, right? As if it were just another table, all right? So yeah, so basically this Q65, right? It's as if, right, you would be embedding that select statement in there, right? If you just replace it in there. Right. So this comes back to an idea with which we had presented early on in our course, right? That we had talked about the level architecture. We had said that databases, modern databases, provide different layers of schemas, right? We have the physical schema, which is the the file system on how the data is being stored in the physically on the device, right? We have the conceptual schema, which in our case it's the relational model, right? That we conceptually think about the data as being a whole bunch of tables that contains a whole bunch of records and rows, right? That are referring to other rows in some other tables, right? That's what we conceptually think of the data structure, right? And obviously, it's conceptual, right? There are no real tables, right? Underneath, right? Everything is zeros and ones. But conceptually, we want to think about it as these tables and rows and columns and these records referring to each other. That's the conceptual way we think about the data. Okay. Or we can think of an even higher level of abstraction as object orientation that has ideas such as inheritance and interfaces and methods and things like that. Again, those are really, really high level ways of thinking about data. Right? Now, but let's stick to databases, right? So yeah, we've been spending the last several weeks, maybe a month or so, about talking about the conceptual schema, right? This relational model. Now, we had also said that modern databases also provide an external schema. And what we mean by external schema is that our efforts for the last month or so has been, what is the best conceptual schema we can come up with, right? And so we drew up some class diagrams, and we talked about redundancy and inconsistency, right? And how we could go about removing those problems. And we talked about first normal form and second and third normal form, and that we should split up big tables into smaller tables, right? Because we want to capture the information only once. We don't want to introduce redundancy, blah, 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 right? And presumably we come up with a best conceptual schema we can come up with, yes? Now, this best conceptual schema is what it's looking to do is try to mitigate the risks of inconsistency and that we are storing and we are retrieving the data as best we can. Now, having it broken up into so many tables might become a cumbersome or inconvenience for actual users, right? When users are going to want to consume the data using some fancy user interface, okay, oftentimes they want to see a nice report, right? And that report might entail, right, coming up with merging together or joining 2, 3, 4, 5 tables, right, to come up with this report. Okay, so oftentimes it's convenient to come up with a virtual way of consuming the data, okay, that combines multiple data sources from multiple tables and then joins them into a useful report. Okay, and views is actually a great way of providing this alternate way of consuming the data and hiding the fact that you have an underlying conceptual schema, right? So different users, whether it's our clients, our partners, or the dean's office or the registrar's office, you might find it very cumbersome to have to, if you want to see a report at the end of the quarter or at the end of the year, having to join 3, 4, 5 different tables. It's very inconvenient. Why don't you put me everything in one single table, which is easier to consume, right? And it's not like we're going to go back and break our normalization only because of their convenience, right? Is that we can instead use views, right, that provides a virtual way of consuming that data without losing the normalization that we so hard work to achieve. Okay, so for instance, we can create a student info or student courses views, right, that combine data from student names, from the enrollments, from the sections, from the courses, right, and combines them into one single view. And here's where we could use the views to create these selections, right, that join multiple data from multiple tables, right, and create these kind of virtual tables that are much more convenient for folks such as the the dean's office or the registrar's office, right, that might not want to consume individual tables, but instead want to consume it at a higher level, right? So views are an excellent way to achieve this. All right, folks, I ran out of time. That's all I had for you. Any questions? So remember, I do have an office hours in about 10 minutes. If you want to continue chatting over there, all right? We can see you there in a few minutes. All right.
Thank you so much. Have a nice weekend.
Thank you. You too. Bye-bye.
Thank you, Professor.
Take care.
Thank you, Professor.
Bye.